Hello viewers, welcome to the channel Amazing Civil Engineering Studies. In today's video we are going to discuss about gravity dam, component and forces acting on gravity dam. What is a gravity dam? A structure that is constructed in such a way that its own weight of the material is used to resist the external force, pressure, created by the water and other materials is known as gravity dam. It is constructed either by concrete or by masonry. Components of gravity dam. Each section of a dam is designed to achieve the self-sufficient weight to resist the water pressure and to protect the structure without any damage. Heel, contact with the ground on the upstream side. Toe, contact on the downstream side. Abutment, sides of the valley on which the structure of the dam rests. Galleries, small rooms-like structure left within the dam for checking operations. Diversion tunnel. Tunnels are constructed for diverting water before the construction of dam. This helps in keeping the river bed dry. Spillways. It is the arrangement near the top to release the excess water of the reservoir to downstream side. Sluiceway. An opening in the dam near the ground level, which is used to clear the silt accumulation in the reservoir side. Forces acting on gravity dam. External forces acting on gravity dam. Water pressure. Uplift pressure. Earthquake forces. Silt pressure. Wave pressure. Ice pressure. Self-weight of dam. Water pressure. The main force or pressure that acts on atom. The water stored creates horizontal forces on the upstream side of the dam. The total pressure created at H/3 level can be collected from hydrostatic pressure distribution. The water pressure distribution at H/3 level will be analyzed for two typical cases. There is no water in the upstream side, upstream face is vertical. There is water in the upstream side, the upstream face is sloping, no water on the downstream side. This is the largest external force acting on the dam. It has the largest capacity for disturbing the stability of the dam. It is a horizontal force which acts at the center of gravity of the pressure distribution diagram, due to water. The pressure distribution diagram is always triangular with zero value at surface of the water and increasing linearly to maximum at the base of the dam. The value of maximum horizontal pressure at base of the dam is W times H, where W is the density of water in kgm3a and DHTHE depth of water in meters. Since pressure distribution diagram due to water is triangular, the value of the total horizontal pressure, P, due to water, will be area of the triangle. This force will act at Cg of the pressure distribution triangle, i.e. 3/h from the base of the dam. Hence, total horizontal pressure equals. This force will act at h/3 from base of the dam. Similarly, if there is tail water of height h on the d/s side, it exerts a horizontal pressure P of opposite nature, where P equals horizontal force due to tail water. H equals depth of tail water from the base of the dam. Uplift pressure. Have you been to the beach? When you are at the seashore, the waves seep under your feet and run off the sand, which makes you feel that you are going to fall. The uplift pressure is also more like that. When the upstream side has water, it seeps through cracks, pores and fissures of the footing material of the dam, creates a hydraulic gradient between the upstream and downstream side. The gradient will create a massive uplift force which will eventually reduce the effective weight of the dam. Silt pressure. Silt deposited on the upstream side of the dam will be analyzed for any vertical forces if the dam is sloped. The silt content deposited will be neglected at first, since there will be no silt deposit on the slanting side. However, after some time the silt deposited on the slanting side will act as a horizontal force on the upstream side, which helps to minimize the uplift force acting on the dam. It can be calculated by measuring the height of the silt deposits on the upstream side. Earthquake forces. In seismic zones or nearby high susceptibility earthquake areas, the dam is needed to resist the earthquake forces. The earthquake creates movement on both the dam structure and the water in the reservoir. So the design needs to be analyzed for the possible pressure by storage water, hydrodynamic and dynamic loads on dam inertia of the dam. Wave pressure. Water stored in the upstream reservoir waves on the surface of the water area by the atmospheric wind. It creates pressure on the upstream side of the dam and pushes towards the downstream. Wave pressure can be calculated by below formula. P W equals 0.5, 2.4 W times H. W 3/8 H. W. For less than 32 km wind load, HW equals 0.032 VV.F plus 0.763 0.271 F, 3/4. For more than 32 km wind load, HW equals 0.032 VV.F, where H W. The height of the water from the top of the crest to bottom of the trough in meter. V. Velocity of wind in km. F. Slate length of water expansion in km. Ice pressure. In cold countries, Western countries, the ice may be formed on the surface of the water. It melts and often expands, which creates thrust force. The dam needs to be analyzed for the possible thrust pressure exerted by the ice forming on the water surface. It acts linearly along the length of the dam. The magnitude of this ice pressure ranges from 250 to 1,500 kN/m2 upon the climate conditions. For ordinary circumstances, it will be considered as 500 kN/m2. Self-weight of dam. Most basic load, dead load, pressure. It is the resting force that resists all the external forces acting upon the dam. It can be calculated by W equals m volume, where m equals unit weight of dam materials. In an upcoming video, we will see the design analysis of gravity dam, where we can use the above-mentioned formula in detail. Thanks for watching. For now, please subscribe, like, share and do not forget to press bell icon.